Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RET 120 Hydraulics. Today we're going to have a discussion about directional control valves, things that we've already used before, but we're going to discuss them in a little bit more detail. But before we do that, I just want to go ahead and revisit the check valve. So as we know, the schematic symbol for a check valve is basically the ball in a seat. Sometimes you'll see a spring there. And again, what does it do? It allows free flow in one direction and stops it in the other because fluid pressure on the back of the ball is forcing it to the seat and it won't flow. So that's one of the applications. You've seen a couple of other applications here. For example, our flow control valve, namely a bypass. That is in fluid flow in this direction. It's going to go through the flow control valve, but it's not going to go through the check valve. So therefore, fluid is limited to that controlled by the flow control valve. Whereas if fluid went in the other direction, we could have a flow rate only limited by what we're capable of supplying, because due to the check valve placement here, it's bypassing. So that's our one way, and that's our bypass application. There's hundreds of different applications for these things. Here's another one. Here's a pump. You expended all that time to get fluid into a passageway. Sometimes you could ensure that there's a prime, basically all that fluid that's been lifted up to here, that when you turn the pump off, you don't want it to drain back through the pump. Basically, the check valve allows fluid flow in this direction, but stops it back in this way. So basically keeping prime. But those are all applications for a typical check valve, but I want to actually go into a little bit more detail about a check valve. What I've got is a little cutaway right here, and this cutaway shows not a ball, but a poppet. For all intents and purposes, it's kind of like a ball. It's just this bullet-shaped object right here that fits in that passageway. And this is a right angle check valve. So previously I've drawn, a ball. Basically direct acting, where fluid pressure on this side of the ball is going to push it out of the way, but the ball is still in the passageway. A right angle is different because fluid pressure here, actually let's use red, is going to push that thing out of the way, push that obstruction, in this case it's a poppet, out of the way. So it's not going to interfere with fluid flow. So that's a right angle check valve. You'll see these things sometimes too. And in this case, it's using a poppet. But let's go ahead and modify this right angle check valve with putting the secondary chamber below it. And the secondary chamber has got a little piston that can move up and down, and which wouldn't really be special until we connect these guys via a little rod that passes through here. What we've got is a pilot operated check valve, which is a little bit different than we've thus far discussed. Pilot operated check valve. So a pilot operated check valve. Pilot is basically, it's receiving a pressure signal from somewhere else in the system. So I'm going to go ahead and clean this up. And then so obviously a check valve looks like this. But if it's a pilot operated check valve, it's going to have our pilot line symbol coming to it. And in this particular case, this is what I've drawn here, is basically a pilot to open check valve. Okay, so a pilot to open check valve. Normally, if it's not receiving a pilot signal, guess what? acts as a check valve, which you would expect. So no pilot, yes pilot. What happens when there's a pilot pressure signal? It opens up. Very simple. Allowing fluid flow in both directions. So how do I know it's a pilot to open check valve? Well, obviously there's a pilot signal, but where's the pilot signal going to? It's going to the open side. You understand what I'm saying? On a schematic, it's the pilot pressure signal is pushing the ball back this way. Okay, so in our little diagram, which we've drawn right here, our cutaway, what's going to happen for this? Well, a pilot to open is going to have its pilot pressure coming in here and push on that side. So if there is, okay, so let's say there is no pressure from the pilot. What's going to go on? Well, it's going to allow fluid flow in this direction, going to block it in that direction. Okay, just like a regular check valve, i.e. no pilot pressure, acts as a check valve. Whereas if there's a pilot pressure signal, it's pushing on this piston, which is connected to this rod, which is connected to the poppet, and pushes it open. Okay, so now you've got, it opens, fluid flow in both directions. Basically our poppet has moved back into this position right here, and it's going to allow fluid flow in both directions. What is this other passageway in the plunger? That's a drain, because if any of the pilot pressure comes back here, or excuse me, any of the pressurized fluid from the pilot port comes back here, it's going to be hard for that plunger to actuate. So you may see the drain symbol, which you remember is a dot, dot, dot. Okay, so now, what if I just reverse the pilot and drain connections here? What have I done? I've created a pilot to close check valve. I'm having some difficulty here. Let me go ahead and clean this up. Okay, I've cleaned it up here. So now my pilot pressure is actuating here, and here's my drain. So when I have pilot pressure, it's holding the poppet down. So pilot to close. If there's no pilot pressure versus when there is pilot pressure. If there's no pilot pressure, again, acts as a check valve, just like it normally would be. If there is pilot pressure, a pilot to close closes. No fluid flow, either direction. Because, as I just said, basically your pilot pressure is pulling down, pushing down on that piston face, and it's pulling the rod down and pulling the poppet to a seated condition, regardless of fluid in this direction. Which normally, if there was no pilot pressure, it would allow flow, but because the pilot pressure is pulling down on that poppet, no flow, either direction. Okay? So, again, what would be the schematic symbol for a pilot to close? Typically, you really won't see the drain symbol on there, but be aware there is a drain connection you have to make for both of these guys. So for pilot to open was on the open side, a pilot to close, obviously, on the closed side. Okay, so that's how you can tell the difference between these two guys. And they again have very similar functions when there's no pilot pressure. Basically, they just act like a check valve. But when there is pilot pressure, the open one opens, the closed one closes. Very simple. Okay, so let's actually get to the heart of this lecture, which is our directional control valve. So directional control valve, basically its whole purpose in life, it's a valve that stops, starts, or changes the direction of fluid flow within a hydraulic circuit. So again, stops, starts, changes direction of fluid flow. And I've drawn a cutaway of a very, very, very simplified directional control valve housing. And this is one of those things where you got to put on your 3D glasses. Here's a directional control valve. And not only are you putting it on your 3D glasses, you're putting on your X-ray vision glasses, because basically what I've done is I've cut this thing down the middle, and we're looking into the innards of this guy. And that's what this is supposed to represent. Again, it's a very simplified version of this, just one type here. So that's the valve housing into which a spool fits. And the spool fits in this passageway right here, okay, which is cylindrical in nature. And you've got these things on it called lands, and the next one is valleys. So basically a land is sized big enough so it's going to bridge the gap between there, and there's enough tolerance, enough clearance in there. It can move, but it's going to seal it off from one side to the next, okay? Whereas a valley, it's this tiny little thing, and fluid can flow around it. So a valley, basically fluid flows around the valley, but it's blocked by a land. It can't get to this side right there, okay? So that spool is a movable item within inside a directional control valve that selectively connects and disconnects the passageways within our valve housing, okay? So I'm going to draw the schematic symbol of the valve that we're going to do here, and this is one of those valves that this is a super common valve. And I know we've done the schematics on these things, had a brief discussion about them, but we haven't really figured out how they work internally. So a directional control valve has a number of positions. Positions is basically the number of configurations a valve can be placed in to pass or block fluid flow. So positions, number of configs. Okay, and in this particular one, we've got one position, two positions, three positions. So that is a three-position valve. The number of ways, synonymous with the word ports. Port is the actual connection, way is the passageway in between it. There's 4 in this particular one, namely P, T, A, and B. And we're going to go into other ones that have less or more. Okay, so number of openings, number of connections. I guess that would be to say number of connections. There's a means of activation. There's always a means of activation, because otherwise if it stayed in that center position, it wouldn't do anything. So there's a means of activation. That's a lever. It's a manual means of doing it. Here's a push button. They're all kind of manual. There's hundreds and hundreds of different one of these levers, push buttons, foot pedals. They're all kind of manual activations. There's manual versus a solenoid, which is, so here's a manual. There's a lever, push button. I'm just expecting you to know probably this guy. but be aware that there's other types of manuals. Basically something that requires human intervention. Whereas a solenoid means of activation, that's the schematic symbol for that. Basically, it is a electrical means of activating a valve. So like I just said about the spool here, that end of the spool, basically, if you've got this little electromagnet here, which is the solenoid, and you've got the spool, and it's de-energized state, nothing's going on, all of a sudden you turn a switch, or a computer turns a switch somewhere. Basically, this coil is energized, it becomes an electromagnet, and the spool is pulled inside that portion of the solenoid, activating that directional control valve through an electrical means. Okay, so that's a solenoid, a means of electrically activating a valve. And very similar to our discussion above about the pilot-operated directional control valve, pilot-operated check valve, you could also have a pilot signal from somewhere else in the system. Basically, it's pushing on some face on the end of the spool, and it in turn is moving the spool. And there is no connection between this portion, the pilot portion, and the functional portion of that directional control valve, because again, that valley is in the way. So the pilot is a means of activating. So what's really neat too about a pilot activation, it's incredible holding pressure. You know, so basically you shift, this pilot signal comes in, and that spool can be held in this direction. Okay, we're going to go into some of the advantages and disadvantages of solenoids and pilot and put them together in a combination called a piggyback in a little bit here. But so we're just having a general discussion about directional control valves. So activation, there's a means of manually or automatically, or using pressure pilot from somewhere else in the system, of moving that spool. The means of centering, I'm going to skip one here. So the means of centering. So if it's a 3-position, you put a spring on one side, put a spring on the other, it's spring centered. Whereas if we had a 2-position valve, it's spring offset. So this one is being held in this position by means of the spring, and it requires pilot pressure from somewhere else in the system to activate it into the other position. Okay, we've seen this thing over and over again. This is a 3-position, 4-way directional control valve that is spring-centered, and let's pretend it's a manual activation. It's a closed center. Closed center, meaning there is no passageway from P to T because they're blocked. And there is no passageway from A to B because they're blocked. And no passageway from P to A or B, no passageway from T to A or B. Basically, everything's closed. All ports are closed. There's no means of fluid passage in the center position. There's a number of different types of center positions, and we're going to go back into some of the other ones that we may have not seen at this point, though. But right now, just pretend that we're dealing with the closed center position, which we are. Okay, so now let's go back to our discussion about our spool and how this thing does exactly what our schematic says. Okay, so let's put a spool, let's put our pretend spool in here. So it's a closed center position. I'm going to go ahead and put that in. And there is our spool in the closed center position. And we got to, again, use our 3D glasses here a little bit because we've got kind of this, let's just do from the pressure. Pressure's going through this underpass right here. And again, it's blocked by one of those valleys from entering either the A port or the B port. Okay? Tank is on the overpass. So to drain to the tank, there's no way A can drain to the tank because there's a valley in the way. There's no way that B can drain to the tank because there's a valley in the way, a land in the way. Okay, so that's our closed center position. Okay, now we go ahead and shift it, and we can shift it one way or the other, either straight through or a cross connect. Okay, and let's see what happens here. And I've gone ahead and shifted that spool, and yeah, I know it's not proportional. I kind of messed around with the proportions of the spool to illustrate this thing. But anyways, straight through position, P goes under the underpass, can sneak around the valley, goes straight to A. T, it drains B, but A is prevented from draining because there's a valley, a land in the way. And again, this spool position there prevents passageway from A to B. Okay, let's shift it in the other direction. And so here we've shifted it in the other direction, and we should be in a cross-connect position. Yeah, and I know I'm playing around with the dimensions of the spool and the location of the B port. The spool doesn't change dimensions. The spool is this thing that looks like that. It's a solid object and moves simultaneously, as we're going to see when we take these things apart. But what does this serve to show? It's serving to show that now we are in P2B, A2 tank. Again, there's no connection here. There's no connection between A and B because of that. And there's no connection from A to the pressure. Okay, so if that didn't confuse you enough with the directional control valve, there's a bunch of, take a real one of these things and take a look at it. It's kind of hard to trace out the fluid flow paths, but ultimately they are doing exactly what this schematic is saying. There's a straight through position, a cross connect, and a closed center position. Here's another example of one, as if I haven't confused you enough on this, if that didn't make you understand what was going on. Here's what's going on here. We've got P, which is blocked off, T, which is blocked off, A, which is blocked off because there's a land on that side and a land on that side. There's no passageway in between. And we've got B, which is blocked off because of those lands right there. So what is that center position? Closed. What are the two other positions? I'm not going to have you do this on an exam too. I'm just giving you an idea what's going on inside a directional control valve. This may serve as a better example than the previous one. Okay, let's go ahead and clean her up and shift it to a different direction. So now we've shifted our spool in a certain direction, P to A. What's going on in this overpass here? Nothing, because there's a land in the way. B to T. What's going on here? Nothing, because there's a land in the way. So we have gotten ourselves to a straight through condition. P to A, B to T. Let's go ahead, clean her up, and shift it the other direction. So we've shifted the spool this way now. Now where's pressure going? P to B. Where's A dumping to? Can't dump there because there is a land in the way. A is going to tank in that direction. Okay, so just a different example of our same closed center position, 3 position with a straight through and a cross connect. Just a different means of cutting it away. So is that the only type of valve available? Our 3 position 4-way spring-centered, manually activated directional control valve? No, there are a bazillion different types of valves out there. For example, here's a two-position, two-way valve that is spring offset and let's say solenoid activated. Now, what is this thing? This is an on or off. I could do this way. This is an on or off for, say, for example, you got several of these things in a row. Let's say you're in a factory. And rather than duplicating a pump for each one of those things, you get a single pump that supplies all of them and associated associated relief valves. And whatever system A does, whatever system B is doing. So basically, that's an on or off button. So turn on system A, what it would do, the solenoid would push or pull that spool into its magnetic field and shift the spool into an on position, namely this one right here, okay? And what's happening with B? Well, if B is not turned on, it's in the closed position, okay? This illustrates not only a two-position, two-way directional control valve, because again, it's two positions, 1, 2, how many ways, an in and an out, 2 ways, okay, or 2 ports. This serves to illustrate not only some basics about directional control valves, but something mega super important that you need to understand not only for hydraulic circuits, but our electrical circuits as well. All schematics are always drawn in the deactivated or unenergized position, i.e. this solenoid is not activated. The solenoid is not activated and it's being spring offset to the closed position. This is what's known as an NC valve, normally closed. Okay? Whereas, what's this valve right here? That is its evil twin, an NO, normally open. Two totally different things. And if you don't know the difference between these two, you will have the increased possibility of getting killed, okay? So, normally closed, i.e. there's a closed position in the unenergized state, and you need to energize it to allow fluid flow, okay? Whereas a normally open valve normally has a passageway, and you need to energize or activate it to close it, okay? So normally close, if you activate it, it opens. Normally open, activate it, it closes. I know this is, just follow the logic here. A normally closed in its deactivated state is normally closed. When you activate it, it opens. Normally open in its deactivated state is normally open, and when you activate it, it closes. Seems very simple, but this is something you gotta get through your mind right now. A valve is in a closed state when it's unenergized. When you activate it, it opens. It does the opposite of what its unenergized state is. And I'm gonna go ahead and even throw something in here to even drive you crazy here. This is not the only way people talk about schematics. On normally closed in the States, I was talking to this German engineer once, a normally closed, he goes, oh, you mean an opener? Drives me crazy, but it's totally true. An opener, when activated, it opens. Whereas a normally open, when activated, it's a closer. So be aware there's a couple different ways of thinking about this. And I'm going to throw something in here that's going to blow your mind. And this is more later in the course that I want to talk about this, but I'm going to talk about it now. A normally closed hydraulic valve, NC hydraulic valve, will not allow fluid flow, as the name implies. What about a normally closed push button? I should actually draw it this way. Electrical switch. A normally closed push button electrical switch does allow electrical current to flow. Okay? Did I blow your mind just yet? Here is a normally open hydraulic valve, and it allows fluid flow to go. A normally open electrical switch does not allow electrical current to flow. Hydraulics, electronics, two different things. We're going to come back to this a little bit later because we are going to go over the electrical control of hydraulic systems. Very, very important topic. Where was I? We're talking about our two-position, two-way directional control valve. And I'm going to go ahead and clean this up here. Okay, so here is a two-position, two-way spring offset solenoid activated directional control valve. And I think I may have already drawn this one to you before. And here is hydraulic system A, it's doing whatever. And what do we notice here? Well, there's an accumulator. Basically, an accumulator is a source of hazardous energy and potentially useful energy for that matter. And we need to go ahead and, if we're going to work on this system, we have to make sure that that accumulator is bled down. What this is implying here, this is a normally open valve. So that means basically solenoid A needs to be energized at all times to close it. Okay? So basically, normal system operation, the pump, what's that check valve doing? It's allowing fluid flow this direction, preventing a bleed back through the pump here. And the accumulator is storing energy. And if solenoid A is energized, it's in a closed position and not dumping to the tank. And it's allowing all those things that the accumulators do, stored sources of energy, developing fluid flow, absorbing shocks, controlling noise, as long as solenoid A is energized. The moment solenoid A is de-energized, it shifts to its normally open state, i.e. it's de-energized and dumps the accumulator. And as long as the pump is off there, you have released potentially stored energy, hydraulic energy, at least in this branch of the circuit. There might be a suspended weight or some other accumulator inside A, so you got to make sure that that thing has been bled off and properly locked out and tagged out. So what if I was to switch this thing, appropriate technical term, to its opposite here. Here is a dump circuit for a accumulator, exact same thing as before, except we're using a normally closed valve. So basically in the de-energized position, we're not energizing solenoid A. It's just sitting there and it's being forced via the spring offset to a closed position. So now we go ahead and pump this thing up there, the accumulator charges up. Okay, let's say we're going to go ahead and work on this thing. We turn off the pump. how do we get rid of stored energy inside the accumulator? Well, we energize solenoid A, it shifts to our dump position, and our accumulator dumps. Okay, so that's the difference between our normally closed and normally open valves, hydraulic valves. Okay, so accumulator bleed downs, ons and offs. Let's talk about a two-position three-way valve. Okay, so here's a two-position three-way valve, namely P, T, actuator A, so 3 ways or 3 ports. What's the positions? 1 and 2. Okay, so two position, 3-way. What's this guy doing? Well, first off, to answer that question, what's this? What's that animal? Well, it's a cylinder, but it's only got one input. It's a single acting cylinder or a ram. And what does this do? Well, when there's pressurized flow here into the cap end, the rod extends because this side is typically vented to atmosphere. And sometimes you may see this drawn as something like this, meaning that's a single acting cylinder where the rod is the same size as the barrel assembly of the cylinder. So it's basically just got a big rod there. And there's no room there. So basically, as fluid fills this cavity right here, it's going to extend. Well, the immediate question is, how do you ever retract something like this? Well, what if you're lifting a house and you were in this dump position here? Basically, there's no pressure. Basically, the house would force that thing down. So basically, single acting ram cylinders retract via the weight of suspended object, or sometimes an internal spring. So retract via the weight of the suspended object or lifted object, or an internal spring. Think of a telescoping ram for a dump truck. It's going to lift the thing up by putting fluid into one end, i.e. the cap end, and then what happens is, well, they basically take that cap end to T, low pressure, and the weight of the dump bed basically forces that single acting cylinder down. Okay, so let's go back into our directional control valve discussion here. So again, this is a two-position three-way. What's happening in our de-energized state, i.e. the spring offset condition? Well, it's retracted because there's no pressurized fluid input to the cap end. We go ahead and shift to our activate position. Pressurized flow goes through here, enters here, and our single acting cylinder extends. If you want to go ahead and drop it, you let go of the manual activation. The spring offset brings it to a dump position. Okay, so that's an application of a two-way three-position valve, which brings us to our old standby, our three-position 1, 2, 3, four-way P, T, A, B. A and B being known as the actuator ports, P and T respectively known as the pressure and tank ports, or pump and tank ports. Let's play around with this guy here a little bit, specifically our center position. And as I play around with the center position, I want you to pay particular attention to what happens at this component. In a closed position, let's say we've set this pressure relief valve, closed center position. By the way, that's what I'm leading up to, is we're going to talk about center positions right now, the different types. In a closed center position, is this relief valve being actuated, i.e. is pressure being dumped across that pressure relief valve from the pump to the tank? The answer is yes, because there is no passageway between here and here because it is a closed center position. And the pressure relief valve has to activate to relieve that pressure. Okay? So what happens, by the way, I did want to say something too. I erased it. I'll draw something real quick here. Here's P, here's T. What's that mean? The X. It's a blocked port. You sometimes may see those X's in a circuit there. A blocked port implies that you gotta block it. Don't just leave this thing hanging there if it's an open inline valve. You gotta put something in there. Because it's still connected, it may still be connected via the internal passageways. So you may want to put in a little plug inside that spot there, or have everything already hooked up with like the male end of a quick disconnect that it is blocked when it's not being connected to a hose. Okay, so that's a blocked port in X anytime you see that. What was I talking about? Oh, we're talking about the center position here. What happens in a closed center position? Obviously, the pressure relief valve is constantly being activated when it's in the center position. And anytime that the straight through condition has extended the cylinder fully and it's reached the limits of its travel, again, it becomes a closed path. Or it's in the cross connect condition and it's retracted itself fully and it becomes a closed path. That pressure relief valve has to activate. And is that the most efficient way of running this pump? So you're holding this thing, and again, you're holding it at 500 psi. It's pretty neat application. This is, you basically lift or pull or push this load and then put it to a center position, and it's going to hold it. As long as those seals in the directional control valve are good, it should conceivably hold it. You might want to put a couple pilot to open or pilot to close check valves in there to maybe relieve the pressure off that directional control valve seals. But what's this pump constantly activating at? It's at 500 psi. That's a closed center position. And it's not the most efficient means because it's constantly trying to force against 500 psi. What if I did the following tiny modification? Oops, I'm going to do different color. The same color. By putting a passageway between the P and T in the closed position. I'll draw that bigger. P, T, A, and B. That is what's known as a tandem. It still holds. But at what pressure is the pump operating now? Well, in a closed position, it had to achieve 500 psi for that relief valve to open. Well, what's your pump at the reservoir, or excuse me, what's your pressure at the reservoir? Ideally, incredibly low. So it's basically the pump is going at reduced pressure, whatever pressure the reservoir is, let's say 20 psi or whatever it is, extremely low. The pump is operating at a very low pressure, i.e. it's operating more efficiently. It's not using as much energy, okay? So that's a tandem. The advantages is basically dumps P to T at tank pressure as opposed at low tank pressures, as opposed to the closed center position. This, by the way, is a tandem. It holds, but it has to dump P to T at the relief valve setting, okay? So just a little bit more efficiency to a system. Okay, let's talk about something else here. Okay, let's say this is a system that objects of varying size are coming into this thing, and you need to hold it. And you would, objects of varying size, you would have to go ahead and activate it and slowly move this rod in for this thing, and then for this thing there. You couldn't do that, or you couldn't grab onto the rod, and move it to hit any one of those objects of varying sizes in that closed center position. So there's this other position, a closed center position, called a float. And I'm going to draw what a float looks like. And that's exactly what a float looks like. The P has got a closed connection. So what's happening there? It's dumping at, our example, 500 psi. So the pressure relief valve is still dumping at a high pressure. But what's neat about here is, what's the A and B pressures? Well, they're connected to tank. And you could theoretically grab onto this rod and move it back and forth. Because if you move it this way, this is just going to dump to tank. If you try to extend it, this is going to dump to tank. A float, what's the advantage? Manually positionable, I don't know how to spell it, so positionable actuator. So you can grab onto the cylinder and move it around in that center position at low pressure. What's going on with the relief valve? Basically, P to T at system pressure, at pressure relief setting. So we gained some functionality in a float position by being able to manually position it, but we're still dumping at that pressure relief setting. So what if we combined the combination of the tandem and the float? That's known as an open. So an open center position, everybody is at the pressure of T. Okay? So if you want to manually position it, either side dumps to T. And additionally, what's that pressurized flow going to? Well, it's dumping back to the tank at the low pressures of the tank. The relief valve does not need to activate. Okay? So what's the advantage of this one? Well, again, it's a little bit more efficient. You are not dumping at incredibly high pressures. Your pump is not working as hard. You can manually position this actuator. And now what's the disadvantages? Well, you would never use this for a suspended load. A suspended load, you probably want to use a closed or tandem center position, okay? Because an open or a float would drop that load, okay? Just think about it. Now here is well, let's go ahead and do this. If these things were both connected to T in a tandem, there is no pressure holding that up and it would crash. And additionally, if it was an open center condition, in a float, the earlier one was a float. I don't know if I said tandem, I think I said tandem. This right here, that's a float. This is our open center. And again, even though pump is connected there, it's going back to T because that's the lowest pressure. And again, all those are at the tank pressure, and that load would also dump to tank and it would fall. Okay, so again, it depends on the application, what you want. All right, there are a bazillion different types of positions in there. These are the most common center positions. Again, our closed, our tandem, float, and our open. There's a bunch of different types of positions out there. I don't want to go over all of them, but here are the most commons. Straight through, cross connect. These are the ones you're going to see 99.99% of the time. The other 0.000009 times you're ever going to see is something called a regen. And at first experience, you might think that the float and regen are the same, and they're not. Because in the float, P is blocked, everything else goes to T. In the regen, T is blocked, and everything else goes to P. Okay? We are going to come back to this guy later in a different lecture, but that's known as a regen position. This is my favorite subject. We're going to go over that in detail. There are other positions out there. There's something known as a proportional valve. A proportional valve, think about the word proportion. Here is our valves in different positions. You've got three choices. Either you're closed, you're straight through, or cross connect. You are never in between them. There is no middle position. And it's full on straight through, full off closed, full on cross connect, or full on closed. There's three choices that you can make. Like a proportional valve is, think about there's an intermediary between here and there. Say for example, this extends our cylinder really fast at like 8 feet per second. Obviously here, it's stopped 0 feet per second. A proportional valve uses basically an infinite position spool almost as a means of flow control, where there is continual variance between this guy and this guy, i.e. the further you pull it towards there, the greater the speed, greater the flow goes through that valve. And conversely, the further you pull it that way, the faster it goes in one direction. Basically meaning that there is a variance between, there's not just a full on and full off. There's full closed, obviously there's a full close, then move it slowly, move it a little bit faster, move it medium speed, move it a little bit faster, move it all the way. That's a proportional valve. Sometimes you'll see this as basically a little joystick control, maybe on some load handling equipment, okay, just trying to gently move something out of the way, and then once you're clear of an object all the way, you can lift it all the way up, okay? So let's check here if I have covered everything on that subject before we move to the next one. Okay, so I want to go into further detail about activation in the means of pilot and solenoid. And let's just start off with our pilot. So here's an example of a pilot activated directional control valve. Which one is the pilot activated directional control valve? Obviously this guy. Which one's the manually activated? Well, this guy right here. And you see what's going on here? When you manually activate this guy right here, it's going to provide pressurized flow via this pump to the pilot line via the straight through condition, and it will activate this directional control valve right here. So basically you're using pressurized fluid flow from somewhere else in the system to control another directional control valve. Sometimes what you might see is basically your pilot, well, what's the advantage here? Basically, is it's all the same system. You're already using hydraulics. So you can just use pressurized fluid flow to hold the pilot activated pressure relief valve in a particular situation. Okay. The other thing that's going on here is, what if pressurized fluid flow inside the pilot doesn't need to be a lot of fluid flow, nor does it have to be at incredibly high pressure. But let's say if you are working with an incredibly high pressure application. Super pump is over here. Baby pump is right here. So basically, baby pump is just providing the tiny amount of pressure to activate that directional control valve, whereas super pump can do incredibly high pressure, incredibly high flow rates. So you might see a combination there where there's a tiny pilot pressure controlling incredibly large pressure in the system. This one also serves to illustrate what a blocked port does. So here's a two-position four-way directional control valve that's spring offset, manually activated. What's happening to that other port there? Well, it's blocked, okay? Because in its unactivated condition, i.e. its normal state, there is no pressure to that pilot valve and it's dumping. In its activated state, pressurized fluid flow is going here and it's activating this directional control valve. Okay, so solenoids, like I said earlier, it's got our spool connected all together, and a little electromagnet, when energized, pulls the spool into it, and accordingly everything else comes with it and changes direction, stop, starts, or change directions of fluid flow. What's the advantage here? What's cool is basically they're efficient and quick acting. Electrical signal, snap, boom, it moves. The other thing is too, you can control this. It's automatic. You can record, using a computer system. Okay, solenoid A was activated at such and such a time. What's the disadvantages? Well, sometimes they're not exactly the strongest things out there. Additionally, you have to, mount these so the spool slides horizontally, as opposed to trying to have this magnet pull the spool up when it's fighting gravity's tendency to pull it down, okay? The holding strength of these things are not exactly the strongest things out there. So there's this thing that you're going to see quite common is a combination of these two, and that's what's known as a piggyback valve. So a piggyback valve uses a solenoid to control pilot pressure to the main valve. I'm going to draw that guy real quick. So there's a piggyback valve, and as crazy as it looks, even crazier, you're probably going to see enclosure signals implying it's all the same thing. And then, yeah, add the connections to it, to the particular portion of the system. It looks a little crazy, and typically the solenoid activated thing is actually drawn a lot smaller. Think about carrying a kid in a piggyback. The little kid is on top of the big valve right here. So what's the solenoid doing? Basically, all it's doing, let's say it's in a straight through position, pressurized flow enters here, shifts it that direction, okay? And again, tank, unpressurized flow allows it to shift. Okay, so basically all of the solenoid portion is doing, that's the solenoid portion, it's controlling the pilot portion of a larger valve. Basically, the solenoid is providing you that quick action that's recordable, you're using a computer system, automatic, again, computer system. You're providing that via the solenoid, but you're getting rid of the disadvantages of the solenoid about being weak and incapable of holding high pressures by giving it the advantages of the pilot. It's strong, capable of holding that position. So a piggyback valve gives you all those advantages. Again, they're close proximity, often drawn in the same device. So if you ever see like a little valve piggybacking, little solenoid operated piggybacking on a pilot, it's pretty obviously a piggyback valve, having the advantages of solenoid and pilot. Okay, the last subject I want to discuss here is this thing called a detent. Anyone that's ever used a log splitter, you see the detent, basically you push the valve into one position and it locks in that place. Basically, that's exactly what a detent is. It locks a valve in position. So you go ahead and activate it with a manual lever, stick it to one side, it stays there until it reaches something known as a kick-out pressure, sometimes. So basically a kick-out pressure, basically it's an automatic release of that thing. So let's say your kick-out pressure is 1,000 psi, you go ahead and slam it to one side, and it's going to stay there. All of a sudden it reaches 1,000 psi, boom, kicks out, goes back to our center position. Okay, so that's a detent. Sometimes a mechanical, it is a mechanical means of holding it in one position. The last subject I want to talk about is mounting these valves. So pretty obviously in the term inline, inline implies that a valve is placed in line with our pipes, tube, and hoses. One thing too is very often on the valve body is engraved a schematic symbol on it. So what is this thing doing? It's allowing fluid flow in this direction. It is not allowing it in this direction because that is the way the check valve is oriented. It basically is, we're using the engraving. Sometimes companies put stickers on these things, and the sticker could be oriented wrong. That's why go with the engraving. Look at the engraving when you're putting this thing in. So don't be fooled by these stickers because they could fall off and someone could put them on backwards. They could be put on backwards initially. So an inline, basically the pipes actually have to thread into the valve, or the valve threads into the pipe, typically the other way around. There's something, obviously there's a disadvantage to that. You might screw up the threads on that thing. There's basically these manifolds or subplates. We've seen these things before. Basically, a manifold, to think of like an aluminum block into which the pipes, tubes, and hoses are connected, and there's passageways drilled internally to this manifold to wherever it has to go to, and our valve goes on top. It's and there's a subplate in there too. This is a manifold, and that's screwed into that manifold. So the passageways in the directional control valve made up with these things in the manifold, and there's a little O-ring that goes in there. And then all you do is screw that down with the O-ring properly seated into that manifold. What's the advantage here? Well, when you screw up putting a pipe, hose, or tube into this thing, you've just damaged the manifold. You can replace that. Whereas if you're doing inline, you've damaged the valve. Okay, so the other thing is it reduces the tendency to, let's say the valve actually dies. It's a pretty easy and quick change out rather than taking all these pipes off and all those hoses off and all those tubes off. You just pop out the old valve, put a new one in. This is not the only way things are mounted. There is some really cool stuff, basically a cartridge valve or a cartridge, the actual activating components. The valve stays there basically, and the actual activating components come out of the valve body, and you pop it back in there. That's a total simplification of what a cartridge valve is too, by the way, but you can take the guts out, put new guts back in. The other thing is a sandwich valve or a stacking valve stack valve, excuse me. And I know we draw our schematic symbols all over the place, but think about this. Here is a stack of valves physically placed on top of each other, like building blocks. And what's neat about this is you get a common P, a common T from and to the pump. Inside this first one, obviously, is our pressure relief valve. And that same passageway continues up to the next valve, which just goes straight through. And what's here in this one is our directional control valve of interest. Why is the directional control valve on top? Because it's the one that breaks the most. So always the DCV goes on top, because you're going to be able to replace these guys, and I'll show you what's going on here. This guy goes back through here. Well, let's pretend this is our flow control valves. We've got some knob here to adjust. And what's going out here? That's our A and B. This is our entire hydraulic system minus our pump, reservoir, and our actuators. Pretty cool, huh? So stack valves, sandwich valves, I'll get a couple of those in lab. We'll take those things apart. It's just a means of saving space. And again, these things mate together on top of each other, making sure that the O-rings are properly in those passageways and not kinked or twisted or damaged. Okay, so it just means of saving space. So that is about it on directional control valves. Not particularly hard. It's just talking about some of the internal workings within these things to understand how they work.